Hi, I am Rashani DeBell, and you are learning algebra.
Hi everybody! In today's lesson we are going to learn how to simplify a radical. Before we get started, let us examine what a radical is and the different properties used to simplify a radical.
Simplifying radicals. Our objective is to use the properties of radicals to simplify radical expressions. What is a radical expression? Radicals are used to express roots in math. The square root symbol is a radical function. Other examples include cube root, fourth root, etc. Here's a radical expression. The square root symbol is called the radical. The number under the square root, the 25, is called its radicand. Properties of radicals. Product property. The square root of a product equals the product of the square roots of the factors. What this means is, if you have a square root of a times b, you can separate it into the square root of a times the square root of b, where a is greater than or equal to 0 and b is greater than or equal to 0. Quotient property. The square root of a quotient equals the quotient of the square roots of the numerator and the denominator. What this means is, if you have the square root of a divided by b, you can separate it into the square root of a divided by the square root of b, where a is greater than or equal to 0 and b is only greater than 0. Writing radicals in simplest form. Just like with fractions where you have to leave your answer in its simplest form, with radicals, you always have to leave your answer in its simplest form. The simplest form of a radical expression is an expression that has no perfect square factors other than 1 in the radicand. Here's an example. Square root of 8 is made up of the perfect square factor of 4 times 2. So I can take the square root of 4. We know that the square root of 4 is 2. 2 is a prime number, so I have to leave it inside the square root. My final answer for the simplest form of the square root of 8 is 2 square root of 2. No fractions in the radicand. Here I have the square root of 5 divided by 16. We cannot have a fraction inside this radical symbol. So I can separate it into the square root of 5 divided by the square root of 16 and simplify the square root of 16 to get square root of 5 divided by 4. No radicals in the denominator of a fraction. Here I have 1 divided by the square root of 4. I can simplify the square root of 4 so that I get 1 over 2, or 1/2.
Now let's look at some examples. In the first example, I am going to show you 3 ways that you can simplify a radical. Use the method that you feel most comfortable with and that you understand when you are simplifying radicals.
In our first example, we are asked to simplify the expression square root of 27. There's 3 possible ways that we can simplify the square root of 27. We could use a factor tree. We could use what I like to call the upside down cake method. And there's also the perfect square factor. Let us first look at the factor tree. To use the factor tree, I'm going to start by writing my square root of 27. When factoring, we are looking for prime numbers that multiply together to make 27. So we start with our smallest prime number. Since 27 is an odd number, I know that I don't start with 2, so I'm going to move on to 3. I know that 3 times 9 is 27. 9 is not a prime number, so I'm going to simplify this further. 3 times 3 is 9. Now that I have everything broken down into its prime numbers, so square root of 27 is broken down into 3 times 3 times 3, I can start looking to see if I have a pair of the same number. Like right here, I can see that I have a pair of 3s. We know that 3 times 3 is 9 and square root of 9 is 3, so I can just take one of those 3's and drop them out of my square root function. This 3 that's by itself, I'm going to write back in to the square root. So the simplest form of square root of 27 using our factor 3 method is 3 square root of 3. Now let's take a look at the upside down cake method. If done correctly, we should end up with the same result as we did with the factor tree with this, which is 3 square root of 3. So let's take a look. To do my upside down cake method, I take my square root symbol, turn it upside down, and write 27 over here. I want to look for prime numbers that 27 is divisible by. Smallest prime number that I can divide 27 by is 3. 27 divided by 3 is 9. And I'm going to continue this pattern over here, keep dividing until I get all the way down to 1. I know that 9 is divisible by 3. 9 divided by 3 is 3. I can divide 3 by 3 and I get 1. And there's my candle. Again, since this is a square root, I'm going to start looking for pairs, because I know if I multiply 3 times 3, it gives me 9. Square root of 9 is 3, so every pair that I have, I'm going to take and drop it out. And what's left over goes right back into the square root. So using our upside down cake method, we got the same answer as the factor tree, which is 3 square root of 3. Finally, looking at our perfect square factor. Now, when using the perfect square factor, we are looking for perfect squares greater than 1 that are factors of our number inside the radical symbol. So we're basically looking for perfect squares that are greater than 1 that are factors of 27. We'll start by writing 1. We know that 1 times 27 is 27. 1 is a perfect square, but we want to look for perfect squares that are greater than 1. 27 is not a perfect square, so this is not a good perfect square factor to use. Let's move on. 2 times a whole number does not give me 27, so 2 is out of the question. Let's try 3. 3 times 9 is 27. 3 is not a perfect square, but 9 is. So I can break down the square root of 27 into, and I like to write my perfect squares first, 9 times 3. I can further break this down into the square root of 9 times the square root of 3. And since I know that the square root of 9 is 3, I can simplify that. I can't simplify the square root of 3 since it's a prime number, so I'm going to leave it as the square root of 3. And notice, using all 3 methods, I still got the same answer for the simplest form of square root of 27, which is 3 square root of 3. In example 2, we are asked to simplify the expressions. We start off with simplifying the square root of 13 divided by 36. Remember, we're not allowed to have a fraction inside our radical sign. So I'm going to rewrite this so that we can see it better. I've got the square root of 13 divided by 36. I can go ahead and break this down into the square root of 13 divided by the square root of 36. Again, I'm not allowed to have a radical in the bottom of my fraction, so I can't have it in the denominator. I can simplify the square root of 36 because the square root of 36 is a perfect square, and we know that 6 times 6 is 36, so square root of 36 is 6. Square root of 13 is a prime number, and there are no perfect squares or factors of 13 other than 1 and 13, and we are always looking for perfect square factors that are greater than 1. Since I can't simplify this any further, this is just going to be the square root of 13. So my final answer over here, the simplified version of square root of 13 divided by 36 is the square root of 13 over 6. In our second example, we have the square root of 48 divided by 81. Can't have a fraction inside the square root, so we are going to break it down into the square root of 48 over the square root of 81 and look to see if we can simplify both the square root of 48 and the square root of 81. I know that the square root of 81 is a perfect square. 9 times 9 is 81, so the square root of 81 is just going to be 9. 48 is not a perfect square, but I can simplify it. So I'm going to use the factor tree method to simplify the square root of 48. I know that 2 times 24 is 48. Remember, I want to break it down into its prime numbers, so I'm going to keep going until I end up with all prime numbers. 24, 2 times 12 is 24. 2 times 6 is 12, and 2 times 3 is 6. Now that I have all of my prime factors, I can start to look for pairs of them so that I can take and drop it. Here I have a pair of 2's, so I'm going to take it and drop it right over here. Times, I notice that I have another pair of 2's, so I'm going to take it, drop it over here. 3 is by itself, so it's going to go back under the radical symbol. And I'm going to simplify this 2 times 2, which gives me 4 times the square root of 3 divided by 9. So my final answer, the simplified form of square root of 48 over 81, is 4 square root of 3 times 9. Finally, square root of 90 divided by 160. Before I break it apart, I can see that 90 and 160 are both divisible by 10, so I'm going to simplify first by dividing both 90 and 160 by 10. When I do that, I get the square root of 9 divided by 16. I can simplify that into the square root of 9 divided by the square root of 16. Both 9 and 16 are perfect squares, so I can evaluate them. Square root of 9 is 3, square root of 16 is 4, so my final answer for the square root of 90 divided by 160 is 3 over 4, or 3/4.
And this concludes our lesson on simplifying radicals. Have a groovy day.